We're surrounded by mixtures literally every single day. The air we breathe, the coffee we drink, they're everywhere. But behind these simple, everyday things is a fascinating world of chemistry. So today, we're going to pull back the curtain and uncover the science of solutions, this hidden chemistry that, well, makes our world work.
Okay, let's just dive right in with a bit of a mystery. What in the world could possibly connect a can of fizzy soda, the dangers of deep-sea diving, and the stuff that keeps your car's engine from freezing solid in the winter? I mean, they seem totally unrelated, right? But I promise, by the end of this, you're going to see the single, powerful scientific idea that links them all.
So here's our game plan for cracking this code. First, we'll figure out that basic connection. Then, we'll see how chemists actually measure what's going on inside a mixture. After that, we'll explore a really important law about pressure, see how solutions can literally change the rules of chemistry, and finally, we'll look at what happens when those little particles decide to misbehave.
So, what's the big secret? What's the connection? Well, it turns out the one thing that connects soda, scuba diving, and antifreeze is that they are all, at their core, solutions. And their weird and wonderful properties are all governed by the exact same set of chemical rules.
Okay, so what is a solution, really? All it is a perfectly blended mixture, what chemists call homogeneous, which just means it's the same all the way through. The main ingredient, the one you have the most of, is the solvent, and everything else that gets dissolved in it, that's the solute. So in saltwater, it's pretty simple. Water's the solvent, and the salt is the solute. And here's the thing that kind of blows most people's minds. Solutions aren't just about dissolving solids and liquids. Not at all. You can have a gas dissolved in a gas. That's basically the air we're breathing right now, or a gas in a liquid, like the oxygen fish need to survive in water. You can even have solid in solid solutions. We call those alloys, like when you mix copper into gold. The variety is just incredible.
But to really understand how these solutions work, we can't just say, there's some salt in the water. We've got to be precise. We need a way to measure exactly what's going on. We need to measure its concentration.
And at its heart, concentration is a really simple idea. It just tells you how much stuff, how much solute, is packed into a certain amount of your solution. Is it dilute, like weak coffee, or is it concentrated, like a strong espresso shot? It's all about the ratio.
Now, of course, chemists need to be super precise about this, and two of the most common ways they measure it are molarity and molality. They sound similar, but there's a huge difference. Molarity is about moles per liter of the whole solution. Molality is moles per kilogram of just the solvent. Now, why does that matter? Because volume changes with temperature, but mass doesn't. So molality is temperature independent, which is absolutely crucial for getting repeatable results in the lab.
All right, we've got the tools. Now we can finally tackle the first part of our big mystery, the link between that fizzy drink and scuba diving. And it all boils down to a beautifully simple rule about pressure.
This rule is called Henry's Law. And yeah, the definition sounds a little formal, but in plain English, it just means this. The more you squeeze a gas on top of a liquid, the more of that gas will dissolve into it. High pressure, high solubility. Low pressure, low solubility. Simple as that.
And your can of soda is the perfect everyday example of this in action. To get it fizzy, they force carbon dioxide gas into the liquid under super high pressure and then seal it up tight. Everything's stable. But the moment you crack it open, psh, you release all that pressure. Suddenly, the liquid can't hold all that gas anymore, and whoosh, the CO2 rushes out as a stream of bubbles. That's Henry's Law.
Now, this exact same law has some pretty serious real-world consequences. For a scuba diver, the deeper they go, the more pressure they're under. This forces more nitrogen from the air they breathe to dissolve in their blood. If they come up too fast, the pressure drops suddenly, and that nitrogen fizzes out inside their body, just like that soda can. It's a condition called the bends, and it is incredibly dangerous. And the opposite happens to mountain climbers. At high altitudes, the pressure is lower, so less oxygen dissolves in their blood, which can lead to serious confusion and weakness.
Okay, so we've talked about pressure, but that's not the whole story of solutions, not even close. Turns out, the simple act of dissolving something in a liquid can fundamentally change how that liquid behaves. And this is where our antifreeze mystery gets solved.
When you add a solute to a solvent, say sugar to water, those little solute particles get in the way. It's like they're tiny little obstacles, making it harder for the water molecules to do their thing, like escape into the air as vapor. This lowers the vapor pressure, and that one little change sets off a domino effect,
changing the freezing and boiling points of the entire solution.
So, let's start with a baseline we all know. Pure water freezes at exactly 0 degrees Celsius. No surprises there.
Okay, but now, let's mess with it. Let's add our solute. In this case, ethylene glycol, which is, antifreeze.
And boom! Look at that. The freezing point just plummeted, all the way down to minus 17.6 degrees. Those antifreeze particles are getting in the way, disrupting the water molecules as they try to lock into that neat, orderly ice crystal structure. They make it so much harder for the water to freeze. And that, right there, is how antifreeze saves your car engine on a brutally cold day.
So these effects, like lowering the freezing point or raising the boiling point, have a fancy scientific name, colligative properties. And yeah, it sounds complicated, but the core idea is actually super simple. It means that these properties only depend on the number of solute particles you have, not what kind of particles they are. It's all about the count. 1 million sugar particles will have roughly the same effect as 1 million salt particles. It's the quantity, not the quality.
All right, so you might be thinking, okay, I get it, just count the particles, easy. But what happens when the particles themselves don't quite play by the rules? This is where we get to the final twist in our story.
Let's take something incredibly simple, something we all have in our kitchens, regular old table salt, sodium chloride. What really happens when you drop that into water?
Well, it's an ionic compound. So the moment it hits the water, it doesn't just hang out as one little NaCl unit. Nope, it immediately dissociates, or breaks apart into 2 separate ions, a positive sodium ion and a negative chloride ion.
So think about what this means. You drop in 1 particle of salt, but you instantly get 2 particles swimming around in the solution. And since we just learned that colligative properties are all about the number of particles, you've just doubled your impact. You get twice the bang for your buck when it comes to lowering that freezing point.
So how do chemists deal with this complication? They have a clever little fix called the Van Hoff factor, which they just call I. Think of it as a correction factor, or a multiplier, that adjusts our calculations to match what's actually happening in the water. For salt, the ideal I value is 2. For other things, it might be 3. It's the secret code that makes all the math work out in the real world.
So when you pull it all together, we've seen how pressure and particle counts are the secret rulers of the world of solutions. In fact, we use these same principles in reverse for things like reverse osmosis, where we use immense pressure to literally squeeze fresh water out of the ocean. It really makes you wonder, right? If we can use this fundamental chemistry to unmix the ocean, what other seemingly impossible challenges, from cleaning up pollution to recovering precious resources, could we solve next?